Hey everybody, today we are looking at section 3.2, Rolle's theorem and the mean value theorem. First, let's look at this quick warm-up, okay? So a function is defined for all numbers and has the following property here, where f of x plus h minus f of x, this should look familiar, equals this right here. So what I want you to do really quickly is I want you to, recall that the definition of a derivative is this limit as h approaches 0 of f of x plus h minus f of x all over h. So that first part right here, that's the numerator of our limit. Okay, so we're going to use that fact and the derivative to continue on. Okay, so the first thing we're going to do is we're going to use the fact that f prime is equal to the limit as h approaches 0. That becomes our numerator all over h, okay, using the definition of a derivative. Canceling out the h's, we are left with this portion right here, and now we can go ahead and direct substitute for h to get our f prime. So f prime is equal to 3x squared minus 5x. Now we can go ahead and use that to find what f of negative 2 is. So if we do that correctly, we should be able to determine that f prime of negative 2 comes out to be 22. Now we're going to introduce theorem 3.3, which is Rolle's theorem. So there's 3 criteria to meet, okay? First, we let f be continuous on the closed interval and differentiable on the open interval, AB. Then if f of A equals f of B, then there is at least one number C on that open interval such that f prime of C equals 0. So meaning we could have a critical number with a horizontal asymptote. Okay, so those are the criteria that must be met. All right, so first thing, we need to show that f is continuous on the closed interval. Second thing, we need to show that f is differentiable on the open interval. If those 2 criteria are met, then we also have to show that f of A equals f of B. Okay, so if we take a look at these diagrams below, this first diagram shows f is continuous and shows that it's differentiable. Okay, we can see that f of A equals f of B. They get that same value there. Okay, so then there must be at least one x value between A and B at which the graph has a horizontal tangent. So meaning we have a critical number that produces a horizontal tangent line. Okay, now this second example, yes, our f is continuous, so that criteria is met. However, if we take the differentiable criteria out, because we're not differentiable at this point, all right, then f still has a critical number, right? That's still a critical number at C. However, it does not yield a horizontal tangent line, so we can't apply Rolle's theorem. Let's look at example 1. For each given function, determine whether Rolle's theorem can be applied. If yes, find all C such that f prime of C equals 0. So find the critical numbers that produce a horizontal tangent, okay? If we can't, we have to explain. So let's zoom in here on this first example. All right, so we're given that function f of x, and our interval is -3 to -1, okay? So the first criteria, we have to determine if f is continuous on -3, 1. So you could go ahead and plug this into y1, or you can just look over here, and we should be able to see from -3 to -1, we are continuous. So criteria number 1, continuous, that is met. Check. Okay, is it differentiable on the open interval from -3 to -1? And again, we should look at this graph over to the right, and we can see, yes, it is differentiable. So that second criteria is met. The third criteria is, does f of A equal f of B? Again, if we take a look at our graph, we can see that, yes, f of A equals f of B. F of -3 equals f of -1. Okay, and they both equal -1 here. All right, so the third criteria is met. Therefore, we can go ahead and say Rolle's theorem applies, and there exists at least one C in the open interval from -3 to -1, such that f prime of C equals 0. So now let's find that C value. So what we need to do is we need to set f prime of C equal to 0. So we can do this on our calculator. It's a good practice. Okay, so in y1, I want you to plug in the function f of x that was given to us. In y2, use the n-derived function. So here's the old version of what it will look like, and if you have a new age calculator, it'll look like this. This is what you're going to plug in. I only want you to graph y2 to find the 0. So graph y2, calculate the 0, and what you should find is you get this x value. So now we can go ahead and make our conclusion that C is equal to that x value, which is -1.3116. Let's take a look at this next example. F of x equals x to the x to the 2/3 minus 1, and we're looking on the interval from -8 to +8. So again, we have to check our criteria. So criteria 1, f is continuous on -8 to +8, that closed interval, and it is, so it meets that criteria. Criteria number 2, f is differentiable on the open interval, and that is a big no. We can see that it is not differentiable at x equals 0. Therefore, Rolle's theorem does not apply since f is not differentiable at x equals 0, and we're done. This leads us to Theorem 3.4, the mean value theorem. So again, there's criteria to be met. So if f is continuous on the closed interval and differentiable on the open interval, so it starts the same way as Rolle's theorem, then there exists a number C in that open interval such that f prime of C equals f of B minus f of A over B minus A. So that part should look pretty familiar to you, that f of B minus f of A over B minus A, that's our slope formula, right? So this is really talking about an instantaneous rate of change, which is that f prime, all right, equaling the average rate of change. So our mean refers to the average rate of change of f on that closed interval AB. So if you take a look, we're really looking at when does this secant line, okay, this secant line equal the tangent line, okay? When are those the same value, all right? So, when are they parallel to one another? So if we take a look at what we're talking about, there's kind of two different ways to look at it. Geometrically, the mean value theorem guarantees the existence of a tangent line at C that is parallel to the secant line through the point A, f of A and B, f of B. In terms of rate of change and that f prime, it's talking about, or the mean value theorem implies, there must be a point in the interval AB at which the instantaneous rate of change, f prime, is equal to the average rate of change, that f of B minus f of A over B minus A, on that closed interval. Okay, so this next example, we're going to sketch the graph by hand and find a point x equals C at which the mean value theorem is true. So when the tangent line is parallel to our secant line, all right? Then we can plot the secant line and the tangent line. And we'll talk about how we would do that on the calculator. So the first thing you should be able to do is plot this f of x, right? And if we did that by hand, at the point 0, 3, we start and we continue on with a curve, and we end at pi over 2, comma 2. So go ahead and show that in, and we'll get to the tangent and secant line in a little bit. So the first thing we need to do is find that c value, right? So by the mean value theorem says, so long that we are continuous and differentiable, which we are, f prime of c is equal to that average rate of change, right? So we go through and we plug in, okay, f prime of c. We can find the derivative of our f of x, which is just negative sine of x, but we're going to plug in for c. And then our average rate of change, we can go ahead and plug in those values. Cleaning things up and using inverse trig, we can get our c value to be this right here, 0.690107. You want to store this on your calculator as a. So make sure you go through and actually plug this in and store that value as a, or whatever you want, really. Now that you have that c value, we can actually go ahead and plug in this slope, or in this tangent line, into our calculator, and we can graph it. So remember, in y1, plug in that function f of x. Now we're going to use the n-derive key. So what we're essentially doing in y2 is we're plugging in the equation of the tangent line. So this n-derived portion represents our slope. Remember that, okay? So we're going to do the n-derive, y1, x, and this is where we're going to plug in a, because we're telling our calculator to calculate the slope at that a value that we stored. Okay, and now we're just using our point slope form. So this whole thing in y2 really represents the equation in the form of point slope, but then we just throw that f of a over to the other side so we can actually plug it into our calculator. If you have questions about this, feel free to bring it to class next time we see each other. If you did it correctly, you should see y1, the function, on your calculator graphed, and you should also see the tangent line at the point, whatever we said a was. So this 0.690107. So you should see that tangent line drawn in. This last example is a challenge problem. So don't worry too much if you have questions, but I'm certainly going to walk you through it because it's a good practice problem. So what we want to do is we want to find all c's, so all those c values, on that interval from 2 to 4.5 that satisfy the mean value theorem, okay, for our function. So are we continuous on this interval? Yes, we are continuous, and f is also differentiable. So now we can apply the mean value theorem and say, okay, f prime equals that average rate of change. So we know f prime of x has to equal 3/5. Moving on and just doing a little bit of work to find what f prime is by taking the derivative, we should get that f prime is equal to 1 minus pi times sine of pi x. Okay, now we're going to actually apply the mean value theorem. So we're going to set f prime equal to that average rate of change, that 3/5. And we're just going to go through and we're going to solve for x. So gathering everything on one side and then undoing that sine function, we're going to take the inverse sine of 2 over 5 pi all divided by pi. And now you can plug that into your calculator. But there's an issue. This value, 0.0406, is not on our interval. Remember, our interval goes from 2 to 4.5. So what we need to do, and here's the challenging part, is we need to shift right 2 pi units. So by doing so, remember, we're going to take what's inside of those parentheses there inside that function, and we're going to subtract 2 pi. So then going through and kind of undoing everything, we get this x value of 2.0406. So that works. That's within our interval. However, did we get all of the c values? Well, if we shift right 2 pi again, and I kind of skipped that first step, but it leads us down to this x value, which goes to be 4.0406, etc., which is still in our interval. If we shifted right 2 pi again, we're going to be outside of our interval, so we don't have to worry about any more than that. So by the mean value theorem, we get 2 C values that are satisfying our theorem, okay? And those are our 2 C values. If you have questions on any of this, please make sure you ask in class next time we see each other. Have a good night. Bye-bye.